program, and the next talk is by Jonathan Leake on counting matchings via the capacity method.
Okay, thanks a lot, and thank you to the organizers for inviting me to give a talk here. So before even starting, I'm just going to quickly say, so capacity is something we already saw today in Nishith Vishnoi's talk, and I'm going to use a lot of kind of similar concepts that he talked about there, and maybe some other things. But I will make one point about the word counting here. So his main goal was to approximate, with some algorithm. And mine is going to be more to give lower bounds, like sort of explicit lower bounds for certain combinatorial things. The methods I talk about can be used in certain circumstances to give approximation algorithms, but I'm going to kind of wash over that or give some references to that sort of thing. Okay. So, this has been talked about already quite a bit. This monomer-dimer model and matching. So let me just first give an outline of what's going to happen here. So we're first going to very briefly go through that. We're going to talk about how it relates to the coefficients of the univariate matching polynomial, how you get log concavity. Just going to sort of briefly talk about this as an intro, then to sort of why you might hope to get certain lower bounds that I'm then going to talk about. Okay. Then I'm going to go through this capacity method due to Gurvits. And the main motivating example for that is going to be trying to give a lower bound for perfect matchings of regular bipartite graphs. If you're familiar with Shriver's lower bound, this is I'm going to give Gurvits' proof of this bound and talk about how actually you can sort of, how he also used his proof to get different bounds than this. But I'll talk about that. I'm going to talk about the method in some general way and sort of show you how his method gives you this bound. And I'm also going to talk about capacity and this theorem that he has about capacity. That's the main ingredient to get this example. Once I'm through that, I'm then going to talk about how you might generalize this method and how you might generalize his theorem, talk about the method, and then the sort of main application of this is going to be a new proof of Csikvári's bound for imperfect matchings in this more general context. This is not any result, I think, that Peter talked about today. Yeah, so this is something besides the things he spoke about. Okay, so let's get going. So a lot of us know what a matching is. It's some collection of edges where no two edges kind of touch at the same vertex. And I'm going to call something a K matching if it contains K edges. So the first thing's a 3 matching, then a 2 matching. Okay. Another term that's used for these things are monomer-dimer arrangements, where the dimers are the edges and the monomers are the extra vertices. Okay. So you can associate a partition function to these arrangements. And basically the idea is to each edge you associate some weight, to each vertex you associate a variable, and then you sum over all of these arrangements, multiplying together the weights of each edge in the arrangement, and then the variables associated to each vertex that are not in the dimer, so the monomers. And I'm going to sometimes use this shorthand where I think we've seen this, a number of speakers have used this shorthand before, where you have like a vector raised to something like a vector, and it means the product over kind of the base to the exponent. Okay. So the first, one big result associated to this that's been very important in everything that we've talked about is due to Hallman and Leake. And it basically says, I mean, it's not written exactly this way, but this is equivalent. It says if you take some positive edge weights and you plug in some negative weights, and then you look at this a polynomial that varies with the x, you get something that's real stable. Okay? And real stable just means that whenever all of your inputs are in the upper half plane, it's non-zero. The original result, right, it's a little bit weird to plug in negative weights here, right? But the original result was in terms of positive weights, and it was in terms of right half plane stability. Okay? So how are we going to try to use this, or what are we going to do with this? Well, the point is somehow that this concept of real stability has pretty strong connections to log concavity. And we're going to try to exploit this fact to get some lower bounds for certain combinatorial things. Okay? And yeah, that's what we're going to try to do. Okay. So the first thing I'm going to mention, which this is also in the paper of Hallman and Leake, once you have this kind of real stability property, or right half plane stability, or whatever property you have, there's a way to turn this into some kind of univariate polynomial where each coefficient ends up being the number of matchings of size k in the graph. Okay, and it's there's a number of ways to see this, but that happens to be one way you can do this. And the point is that real stability of the original polynomial means that this thing that you get out at the end only has negative roots. Okay, it's a little bit weird with this square root, but the point is that in the original polynomial you only have terms of total even degree, and so you maybe plug in a t everywhere or a root t everywhere, and you actually end up with a polynomial. And the thing that you get at the end of this is, like I said, this kind of version of the univariate matching polynomial where the kth degree term is the number of k matchings. And since you only have negative roots, you get Newton's inequalities, which basically says that this sequence of coefficients forms an ultra-log concave sequence. So the point of me going through this is this is just to demonstrate one way you can get some kind of log concavity property out of real stability. Okay. And you can see how, right, this is not, maybe if I want some absolute bound on the number of k matchings of a graph, this is not that great just because, right, somehow this says that I can get a lower bound on the number of k matchings if I know something about the matchings of slightly different sizes. But maybe we can use some more general version of this thing, or we can sort of generalize the idea of what it means to be log concave and see if we can maybe get something a little bit different. So at this point then I'm gonna sort of move on beyond that. So like I said, can we get some information on k matchings? Let me get to that in a second. Can we get more refined bounds on these coefficients? Maybe we're going to have to maybe restrict a specific g, because in general getting some bounds on these coefficients is well, it's not, certain things are not known, but it's probably, well, it's going to be a lot harder. So we'll probably have to restrict a certain g. But maybe we can use some generalization of log concavity to figure this out. Okay, and I just want to make a comment here. So these Newton's inequalities come from real rootedness, but it turns out for people who have been here for this semester, there's been a lot of talk of these other polynomials, these completely log concave, strongly log concave Lorentzian polynomials, where you also get these inequalities and similar things. Okay, so just as an FYI, those of you who have been around for that. So like I said, right, let's try to generalize these log concavity properties. We know that real stable multivariate polynomials have some properties beyond just these Newton's inequalities. Maybe we can use these to get what we want. Okay. Okay, so I'm going to now move on kind of in another direction. This was just to sort of maybe set up why we might expect to have these sort of log concavity properties in the situation that we want. Are there any questions before I kind of move on to the next thing?
Can you say what a Lorentzian is?
Oh, okay. Lorentzian polynomial. A Lorentzian polynomial, it is some generalization of real stable polynomials, which basically says, I mean, one way to characterize them is to say that if you take they have non-negative coefficients. If you take any directional derivative so let me start over. You have a polynomial with non-negative coefficients. It's log concave in the positive orthant. And if you take any number of directional derivatives in the positive orthant, the thing that you get back is also log concave in the positive orthant. So it turns out that these, it's maybe just from the words I said, it would seem reasonable that these would have something like Newton's inequalities. And these turn out to be a pretty natural generalization of real stable polynomials that a lot of people here have studied. Okay. So then let's shift gears, like I said, and talk about Gurvits' approach to this problem of lower bounding bipartite perfect matchings. Okay. So let's say we have some d-regular bipartite graph on two n vertices. Okay, something like this. Here d is 3 and n is 4. Okay, and you can construct this bipartite adjacency matrix by basically associating to each row one of the vertices on the top and to each column one of the vertices on the bottom. And for instance, if you look in the first row, this gives you the information of which vertices the first vertex on the top is matched to. So right, it's matched to 1, 2, and 4. That's why you have 1s there. Okay, and if I'm going to pick out a perfect matching, okay, it's hopefully that red, you can see that red. it's going to look something like this. So I've picked a perfect matching over here, okay? And I associate to it certain 1 entries in this matrix. And for it to be a perfect matching, it means that every vertex on the top will be associated to, will have 1 edge coming out of it. Every vertex on the bottom will have 1 edge coming out of it, okay? And so that's going to mean that, right, every row and column of this matrix, there'll be one that's selected, okay? And so what this means is to count perfect matchings, as I'm sure many of you know, it's the same thing as computing the permanent of this matrix, okay? And so we're going to try to get some bound on this. Again, it's going to end up being Shriver's bound, but we're going to come to it using a different proof. And I'm just going to point out something here that deregularity comes into play in the sense that this matrix has this, what I'm going to call doubly d-stochastic property, which is a sort of maybe abuse of the word stochastic here, but it basically means that the row sums and the column sums are all d. Okay. So I don't really need to explain how this polynomial comes into play. Nishith did a good job of talking about why this is related. You basically take linear forms associated to each row and you product them together. And the point is that if you take a bunch of derivatives of this, you end up getting the number of perfect matchings. Okay. So, right. And so the idea is somehow then we have this problem that we know is going to be hard, right? This is picking out some particular coefficient of this polynomial. The polynomial is very easy to write down and to evaluate, but somehow approximating this we should only be able to approximate this coefficient. We shouldn't be able to explicitly compute this coefficient. So I just rewrote the last line we had there. Okay. So and some more information about this polynomial that we have. Right? The thing that's going to link up to these log concavity properties at the end of the day is the fact that this polynomial is real stable. This is easy to see because if aij are non-negative numbers, then if I plug in any elements of the complex upper half plane into xj, right? Each linear form is just going to be some convex combination or positive combination of upper half plane elements. So I'm just going to get a product of things in the upper half plane, which is always going to be non-zero. Okay. So this has some real stability property. So we're thinking this is going to have some log concavity property. And we also know that this derivative preserves this property. Okay? So the fact that the derivative preserves real stability is a classic result called the Gauss-Lucas theorem. And then the fact that plugging in 0 preserves it is also very easy to see. There's a chance that maybe by doing this we're just going to get the 0 polynomial, but we're not really worried about that. We'll just assume that counts as real stable, even though it has zeros everywhere. But let's just not worry about that detail. But the idea is that this is going to set up some nice inductive structure, right? The hope is now, right, we have some real stability, real stable polynomial. It has some log concavity properties. We're going to apply this derivative. It's going to preserve these log concavity properties. And if we can keep track of something related to log concavity along the way, right, after we apply all n of these to every variable, we're going to be left with a number that we want to bound. Okay, so this is going to be the general plan. Okay, we're going to associate some useful analytic quantity to this polynomial, this particular one, and hopefully to real stable polynomials in general. We're then going to keep track of exactly how this operator affects the quantity. Okay, so we apply this operator. Hopefully we can get some bound on how much this thing is going to change. Okay, and then after we apply this to all the variables, we're going to be left with the quantity we want to bound. And so, right, if this all works out in the way that I'm sort of vaguely saying here, it's going to be really great because we'll end up getting some lower bound. Okay. And it turns out that this useful analytic quantity that we're going to analyze and discuss is this notion due to Gurvits called capacity, which we already saw earlier today. Okay, so this is the setup. This is the idea of how we're going to go about this. Okay, so this is how it was defined earlier, and maybe it was a little bit. I can't remember if it was a little bit less general than this. I can't remember if there was this alpha involved, but I'm going to define it this way, where you have some polynomial in n variables with non-negative coefficients. You have some alpha vector with non-negative entries. And I'll define the alpha capacity of P to be this infimum over the positive orthant of evaluating P divided by this sort of product of powered variables. Okay? And so before I kind of get going on how we're going to use this, I want to stop and talk about a few properties that this capacity has. Over my course of reading Gurvits' papers and trying to generalize this sort of thing and figuring out exactly what's going on with capacity, it sort of starts off as a very mysterious thing. I don't exactly, right, you don't look at this and think to yourself, I'm going to be able to get combinatorial lower bounds out of this. At least I don't. But it turns out that there are some combinatorial properties of this and also certain probabilistic and other things that sort of enable you to by keeping track of this quantity, get again, combinatorial bounds. So let's just see a couple of kind of the properties of this that might suggest that something like this is possible. Okay. So the first one I'm going to mention is just a sort of combinatorial property, which is maybe, at least to me, is a little bit surprising. So this capacity, right, you always have positive coefficients and positive numbers you're plugging in, so it's always going to be a non-negative thing. Okay. But it turns out that it's going to be positive precisely if alpha is in the Newton polytope of P. And if you don't know what the Newton polytope is, you just kind of take vectors associated to each monomial in the support of your polynomial. So if I have like the term x1 squared x times x2, then I look at a vector like 2, 1, and then maybe zeros for other variables. And for each term, I make one of these vectors, and I look at the convex whole of those vectors, and I get this polytope associated to the polynomial. Okay? And the fact is that, and it's not hard to prove, the fact is that if alpha comes from this polytope, you get something non-zero, but this is if and only if. And so the reason to me why this is surprising is because this says that capacity as a function of alpha is like a non-continuous function, right? If you go to the boundary, this polytope is a closed thing. If you go to the boundary, it will be non-zero, and as soon as you step off the boundary, it will be
discontinuous, not smooth.
What?
Discontinuous.
Did I say? What did I say?
Not continuous.
I said it's discontinuous. It's not continuous, right?
Capacity is continuous.
But not in alpha at the boundary.
In alpha.
Right? If you move past the boundary, you go from a positive number to 0.
No, of course the Newton formula.
Yeah, on the polytope it's continuous. Yes, I agree with that. But the point is this fact is somehow like, even though I don't know, this is a very analytic thing, somehow it's picking out the polytope, which is, if you think of alpha as coming from r plus to the n, right? As soon as you leave the polytope, it goes immediately to 0. So this is somehow, it wasn't sort of expected to me just by looking at this. Another sort of property is something that I'll refer to as probabilistic, and I'm gonna use some words here associated to probabilities that kind of give me intuition for what's happening here, even though if maybe sometimes, depending on the polynomials we look at, they're not going to make as much sense. This is sort of more like giving me a sense of what's going on. So I'll say the explicit thing. So the first thing to notice is your capacity is always going to be less than the evaluation of the polynomial at 1. And this is easy to see by just plugging in 1 here. And it's an imp, so it's going to be less than that. But the point is you get equality if and only if your alpha vector is this. Okay? And the way you want to think of this is the following. So if P were the probability generating function of some distribution on finite subsets of the numbers 1 through n, okay? If so, the coefficient to a certain monomial is the probability that that monomial, the exponent of that monomial is picked as a subset of 1 through n, then this quantity is exactly the marginal probabilities of that distribution. So the probability, right, it's a vector, so the first entry of that vector is the probability that if I draw a random set from this vector, the probability that x1, like the first element of 1 through n, will show up in your set. So somehow this has some relation to certain, right, if P can be represented as some probability distribution, this has some probabilistic interpretation. And more generally, I'm going to refer to this quantity as the marginals, but maybe always keep that in mind that it's actually that, even if P is not something that necessarily, it's easy to see that it's some probability distribution. For instance, if P has terms which have the degree in certain variables greater than 1, it's not exactly clear what it's a probability distribution on. And in fact, the marginals might even be like greater than 1, so maybe it doesn't make as much sense. But the intuition comes from this situation that I'm telling you about, when P is the generating polynomial for this distribution. Okay. But in any case, then somehow it picks this out. It's maximized at that place. Okay. This one I'll kind of brush over. It turns out that something related to the capacity is the convex conjugate of something related to the polynomial. So this is a function now of alpha. And this is related to certain convexity properties that you get that, again, Nishith talked about earlier today. And how you can use these things under certain circumstances to maybe get some approximation algorithms. And the last one, which I think is maybe the most non-trivial of all of these, which is very related to this, and actually the number 2 and number 3, is somehow, and again, Nishith talked about this earlier, somehow the capacity is something like this max relative entropy, right? That's kind of what the value of this is. So if, again, we're in this situation where P is some probability distribution, and I take the supremum over all distributions with these appropriate marginals, then the maximum, I guess you could say, negative relative entropy is going to be exactly the log of the capacity. So I'm mainly going to be using this property, this probabilistic property in what comes next. That'll be the main thing that we'll need. But these are maybe some general vague intuitions you might have about capacity if you've never seen it before, or you're trying to understand exactly what's going on. There's sort of there's even more kind of properties like this that all kind of fit together. Okay.
Sorry.
Yes.
Quick question. So, about what class of P's
Are these things true for?
are these true for, or can I always scale so it is some probability generating function?
So these things, well, the vague versions of these things are true for any polynomial with positive coefficients. You can scale things to make P of the all ones just be 1. It's just that usually when I'm talking about P being a probability generating function, I mean it in the sense that it's a multi-affine polynomial. Like the degree of every variable is at most 1. So that literally a term is like the subset that you're picking out with whatever probability. But these things, again, if you sort of just now define the marginals to be this, these things are true for more general polynomials with not just degree at most 1 in every variable. It's just, and I guess there's probably some probability distribution you could associate to that, where now you're taking multi-sets or something like this.
General thing.
Yeah, okay.
It's true for any polynomial with no negative coefficient.
Yeah, these are true. It's just maybe the interpretation is a little less, I don't know. It's the classic probabilistic interpretation has to do with subsets of this finite set. If you consider maybe multi-sets, and now like when something shows up multiple times, you allow like the marginal probability to be scaled in that situation, then this is still true. But you have to define the marginals in that way, which is exactly what's going on here. Okay. So now then, maybe you have some intuition of this thing called capacity, maybe you don't. But the point is now we're going to like try to combine this capacity with real stable polynomials and see what we can get. So the main theorem of Gurvits that I'm going to talk about for this method is the following, right? If you have a polynomial P where the degree and the number of variables are the same and it's real stable, and if you know that it's degree at most D in the kth variable, then you get this bound. Okay? And I'm not going to talk about the proof of this. All I'm going to say is there is a way, like the original proof that he did was very elementary actually. It was just kind of basic calculus to get this proof. I mean, the real power of this is coming up with the right notion of capacity. I mean, that's the real thing here. Like you can then go, once you know what to do, proving this becomes relatively straightforward. It's really coming up with the right quantity to keep track of. But the point is, I'm going to give a generalization of this result, which is basically going to rely on this log concavity property of real stable polynomials. So you should think of this being related to log concavity of real stable polynomials.
By the way, the very first proof which I had for that was crazy. It used actually Silhor scaling for matrices.
Okay.
Eventually it was simplified.
Huh. Yeah, I don't think I've seen that proof. Is it?
If you go to the first paper in archive, so if somebody will write a biography, it will get that.
Sure. Yeah. Sure.
So you can see that Silhor, the proof was crazy. Just Silhor
Sure. Yeah. Wow. Yeah. I mean, the proof I know is much more elementary than that.
No. Eventually, yes, it's got simpler.
Yeah. Sure. Huh.
And there was a proof using Newton inequalities. It was after
Sure.
That,
Yeah. Which again, Newton inequalities. Another. This is all sort of related to some underlying logarithm cavity. Okay. So how are we going to use this? Well, it's pretty simple. So the first thing I'll just mention, just so that the next line makes a little more sense. I'm hiding something a little bit here with these ones. So by bold 1, I mean the all ones vector, but I only mean it for the variables that remain. So there are n variables here, so this is going to be length n. But somehow here I've removed the kth variable, so I just mean n minus 1 ones where the kth is removed. Okay. So the point is then, by the time that you spend all of your derivatives on this polynomial, okay, you're left with no more ones in this capacity vector, and you are just left with the value that you get. Okay, so you have that the number of perfect matchings is a bunch of derivatives applied to PG. You apply this bound inductively to each derivative that you use. Okay, and at the end of the day, you pick up n of these, right? And then with this, by the time you're finished, you have no more derivatives. And so that's what you have, right? You have the number of perfect matchings is lower bounded by this constant from all n variables here times this last capacity factor. And the reason why you can always, it's going to be this to the n is because of that d stochasticity property, right? The d regularity of the graph is the reason why it's going to be a degree at most d in xk. And just as a quick illustration of this, because this will sort of come up later, if I have let me write down some very basic graph here. Okay? And if I write down then the matrix associated to this, okay? And then I write down the polynomial. I'm going to write it in this sort of matrix form. All right? So the idea is then, what is going to be the degree? So this is a homogeneous polynomial, degree 3 and 3 variables. What's going to be the degree of the ith variable? Well, let's look at x2, for instance. It's going to be the number of times x2 shows up in each of these terms. So in this case, it's going to be 2. But in fact, the degree is actually just going to be the column sum. Or more generally, the number of non-zero entries in each column. Okay. So this is another, again, this is something surprising to me because I think of capacity as some analytic concept, maybe a priori. And yet somehow, like, some kind of information about number of non-zero entries is coming into this analytic bound, right? So to me, number of non-zero entries is something pretty combinatorial. This is something pretty analytic. It's maybe a little bit surprising that it would come into play like this, in my opinion. But the way it comes into play is precisely in the degree. Okay. So we do this. And then the last thing we need to do is try to approximate, or at least compute this. And what we have in this case is something really nice. We can compute these marginals exactly. And the d stochasticity basically just implies that these marginals is just the all ones vector. And again, it shouldn't make sense somehow that marginals would all be 1, right? Doesn't that mean that like the probability of everything is 100%? But again, this is some generalized marginals. The fact that we don't have something that is multi-affine here means that this makes more sense. So this we can compute exactly based on this deregularity. And so then we just plug in 1 to get the capacity.
By the way, in this form, it's easier to write down, but in this form, it's not sharp. Because the degree is actually getting...
Yes.
And if you carefully write down the inequality, that actually you get something which is sharp.
Okay.
Which is, again, was not in the original paper.
I see. So, I mean, yeah, I guess in general, I think the point that Leon is making here is that you can keep track somehow of the degree of each variable, but you know that, say, after I apply a whole bunch of these derivatives, it's going to drop the homogeneity degree down. And if that gets below d, then I can use that number instead of d here.
Even slightly better you can do, but anyways, you get sharp.
And even better. So by keeping track of more degree information and doing some other things, you can get sharper bounds than this. This is maybe more just a explanation of what we're planning to do for this next application. Okay, so let me just recap here a little bit. So the idea was we started off with some polynomial. We could compute its capacity easily. We had some linear operators we applied. We knew how that changed the capacity. And at the end of the day, we got something that we wanted to bound. Okay, so the part that I was able to generalize here is, right, somehow Gurvits' theorem was for a very specific differential operator, just this one, which then had a very nice implications. Okay, later Nima and Cheyenne, I don't know if they're here, proved something more general for a huge class of differential operators. In fact, they proved A bound for all differential operators. It turned out not to be quite the tightest thing you could get. So they have some result like this, except this now becomes certain stability preserving differential operators. Okay, and this becomes something else. But it turns out that basically you can generalize this to any, roughly speaking, any real stability preserver. Okay, and that is this result. Okay, so if T is some, I'm going to call non-degenerate real stability preserver, and you have these vectors, then there's some constant that is going to bound the capacity of the capacity of what you get when you apply this operator T to P. And you're going to get some universal K for any real stable P, and this K is going to be tight. I'm not going to write it down here, but it has some explicit formula in terms of alpha and beta, and in terms of, if you're familiar with this, the Borchea-Rondin characterization, it's also in terms of the capacity of the symbol of T. Okay, and by non-degenerate, I just mean that your symbol is real stable, so you can talk about this. Okay, if you don't, then just there's some constant that we have a formula for. Okay. So the way that I typically interpret this is that this is some kind of analytic extension of that characterization. The idea being that, right, if you have some operator T which preserves real stability, not only does it preserve real stability, but also it preserves capacity. Right? That's maybe one way you could say this. There's some bound a multiplicative bound on how much capacity can go down. Right? And this fact is exactly the fact we used, or that Gurvits used, in the proof of the previous theorem. Right? We successfully used this property, and this gave us some lower bound. Okay, so that's how I think of this. And it turns out also this is some generalization of an inner product lower bound for real stable polynomials. Like I said, this is due to Nima and Cheyenne. I'm not going to talk too much about this, but again, the point is that lower bound, you do some big inductive process to get down to some really basic base case. You use the strongly Rayleigh inequalities, which you should think of as multivariate log concavity, to prove this lower bound, and somehow this result is some big generalization of that base case. So again, this is all relying on these log concavity properties of real stable polynomials in a really strong way. Yes?
So the capacity itself, if you apply it to a real stable polynomial, is that some additional interpretation, or you just...
Like from the fact that the polynomial is real stable?
Real stable.
So again, what is the question?
I don't know.
If you calculate the capacity of a polynomial, but if you assume that it is real stable, is there some additional nice point?
Well, there is something. So if you will go to please to the definition of capacity. Yeah. So imagine you have here alpha sol equal 1, okay? And what you do, instead of writing this thing in infimum over positive numbers, take absolute value of polynomial and infimum when real parts only positive. Okay? Then it's like complex capacity. And that quantity will be just responsible for real stability. It's happened to be that in a real stable case, the complex definition is equal to this one. In general, they're not equal. So again, you extend this definition considering taking absolute value and taking infimum over real parts positive. Okay? You get some quantity. Okay? Sure. If that quantity is 0, you don't care. But if this quantity is positive, it means that your polynomial is...
Well, it couldn't have been 0 anywhere halfway.
Yeah. And it means that if it's... You don't assume that the coefficients are non-negative. But
sure, it would come out. Yeah.
And so then that complex capacity becomes kind of a measure of stability.
Sure.
Yeah.
Huh.
And it's happened to be that in a stable case, if you know that this number is positive, that this real equal to... In general, they're not equal. So this is one of the problems. peculiar situations.
Yeah, so the idea basically is you can extend, under certain circumstances, you can take this inf to be over a whole half plane, and then you put absolute values around this. And if this is, if your polynomial started off being stable, then this ends up being equal to the original capacity. And in fact, it being non-zero is a certificate that it is stable. So that's the idea there.
So, question about it. So there's nothing that's saying what alpha and beta are with respect to each other. So does this say they're bounds on both directions?
So alpha and beta can be anything, but so I'm hiding a lot of things here. If you pick some alphas and betas that you expect to be like combinatorially problematic, then this k will just end up being 0. So the point is somehow you will always get, there's an explicit formula k, you'll always get something. It's just that if you pick alpha and beta to be kind of problematic, it's just going to be 0 because that is the tightest constant for that pair. So it comes out in the expression of k, but and you can reverse them. Again, it sort of depends on your t and which alpha and betas you're looking at, what exactly is going to happen. Okay, so getting back to this again, I'm just going to make a few comments about this, which I'm not going to have time to go through. But like I said, I already said this. This is very related to log concavity, and another thing, there's this paper of Damien and Nishith from a couple years ago that basically shows that the expression that you get in this lower bound is sort of, if after some kind of change of variables and taking logs and things like this, this is exactly the Bethe approximation. Okay, and the point is they use this to show that if you have a partition function where the polynomials involved are real stable, then you actually get that the Bethe approximation is in fact a lower bound for the actual partition function. And the way they do this is they transfer the Bethe approximation into this question about inner product lower bounds, and then they use this result of Nima and Cheyenne to show that this in fact is a lower bound. So again, I haven't given this inner product bound here. I just talked about some generalization of it, but somehow this is also generalizing this somehow. So I don't know. I don't actually know exactly, but if anyone has any maybe intuition about that, if they've seen this stuff that I'm talking about, I'd be interested to hear about it. Okay. So let's move on then. So I think I have about, what's the time? About 6 minutes, is that right?
Yeah. 7.
7. Okay, great. Okay. Okay. So let me just then quickly talk about how exactly we're going to apply this to counting, in particular, this kind of lower bounding thing. But again, a lot of this stuff can be used for approximation. So let me just go through this. So we're going to take that plan we used before, and now we're going to just generalize it with respect to this result I just gave. So we're going to start with some stable polynomial that somehow encodes the object we care about, and this extra added fact that we can compute capacity for it very easily. Okay, so we have this starting point. We apply some operators which preserve stability, and now we can use much more general things here, and we can determine from this constant k exactly how the capacity changes under this operation. And at the end, fingers crossed, we're going to get something back which is now just a constant polynomial, just some kind of constant. That's exactly the thing we wanted to bound. Okay, so this is exactly what we did before, but now we have much more options for the type of operator we can use. Okay. And if you're approximating, you might want an upper bound as well. There's a sort of result in this direction in this paper that I referred to, but I'm not going to talk more about that. I'm just mainly interested in lower bounds. So now we're going to shift to this slightly more general situation, which this is the situation that Peter Csikvári considers. So let's suppose now we have this biregular bipartite graph. Okay, where now the bipartitions are different sizes. And the regularities are also going to be different, right? It's 3 regular from the top, 2 from the bottom. Okay, and we write down the matrix in the exact same way. Rows correspond to the top, columns to the bottom. So we now have a rectangular matrix. Okay. And we can do similar things, except maybe we want to count imperfect matchings now. So let's say I want to count the number of 3 matchings. Well, let me write one down. There's a 3 matching. And what a 3 matching is going to look like here is a collection of 3 rows and columns that contain exactly 1, 1. Okay? So more generally, right, if we generalize the fact that the permanent counted perfect matchings, right, The number of k matchings then is going to be the number of k subpermanents. So you take all k by k submatrices and you compute the permanent of each of those and you sum them all up. Okay. And another generalization of what we got for deregularity is the fact that now, right, if I'm AB regular, it means my row sums are going to be A, my column sums are going to be B. So it's looking like we can probably generalize this whole thing, but let's see what happens so we can write this polynomial down in the same way before. Okay. So I'm going to switch gears really quick because I'm going to talk about exactly what Peter obtains for this, and then I'm going to sort of go back to this picture. So this is the type of thing we want to count, and what he gets is this sort of bound. Unfortunately, I'm not going to be able to talk about it very much at all, but I will just give you some intuition about it. So this H is some entropy function for some infinite biregular tree. PK is something that I'm not going to be able to talk about. I actually have very little intuition for it. So this is some extra factor that maybe comes out. Okay, but the point is why you would expect this entropy function to show up is basically this intuition. So you have this you have this bipartite graph. You want to count matchings on it, and the intuition comes from the following sort of idea that small odd cycles in a graph produce less matchings, and small even cycles in a graph produce more matchings. Okay, and if we're in the bipartite case, we don't have any odd cycles, so we can sort of get rid of that. But then, as soon as we don't have any odd cycles, sort of the worst case situation is that we have no small even cycles. Right? If we have no even cycles at all, then somehow we intuitively should have the least number of matchings possible. Okay, and so somehow the worst case is, if we're going to lower bound, something that's sort of like a tree, and maybe this is some general idea as to why you'd expect something like the infinite biregular tree to appear in the lower bound. Okay, I'm going to sort of just brush over that. I only have a few minutes here, but that's kind of the intuition for this bound. Okay. And it turns out this bound translates into, if you do a bunch of algebra and computations, you get something that looks a lot like Shriver's bound, but it's a lot more complicated. There's like, an to the power an times some b something to the power whatever multiplied by a lot of things. From this pk, you get some from this Bernoulli thing, you get some n choose k. Okay, I'm not going to write down the actual expression here, but you get some complicated algebraic thing that you can convert from this. And this is the sort of thing then that looks like something like Shriver's bound. It looks like something you could get out of this capacity method. Okay. So, like I said, not as clear. Okay. So let's try to emulate then what we did before. Okay. So we had this polynomial. Okay. We had the perfect matchings. We're this big differential operator, but now we have to do something a little more complicated. We have to write. This is somehow what are we going to do? We're going to take kth derivatives, and we're going to take all possible combinations of kth derivatives. So you, out of 1 through n, you pick k, all possible k things. You take those derivatives, those k successive derivatives, and then you sum up all those possible things. The problem is now, right, let's suppose I'm in this situation, and I'm taking 2, right, my k is 2. Right, maybe I take derivative with respect to x1 in this. I take derivative with respect to x3 in this, something like this, and I'm left with some linear. Right? If k is less than n, I'm going to be left with some homogeneous polynomial at the end of this. So plugging in 0 is out. Right? We can't plug in 0. That's going to be a big problem. It's just going to zero out everything. So maybe we plug in something else. Maybe we plug in 1. But I don't, maybe a priori it isn't, why are we plugging in 1? Okay, well, we sort of get lucky in this case. Since we have regularity, once we apply a bunch of derivatives, we're going to be left with some big sum of products of linears. And we know that each of those linears have terms that sum to A. Right? We had this A regularity property. Okay? So we're applying this to PG is just going to give us the number of k matchings times some extra factor that comes from the fact that we had to plug in 1. Okay? But the note here is that already we're requiring regularity of the graph. Before, just writing this down for any matrix was computing the permanent. Okay? Now if we want to compute a bunch of subpermanents, right, we at least to write something down explicit, we already need some kind of regularity property. Okay? Again, for something explicit.
By the way, this is the formula which was used in Cadiz and Singer. So it's instead of evaluating at 1, you can evaluate at 0, but take 1 minus partial derivative product of those guys.
Sure.
It's exactly was their expression for matching polynomial.
Huh.
In that case, instead of linear forms, it was determinantal.
Right. Yeah. I guess I've never. I'll have to think about that.
Yeah, okay. But isn't this the formula that Schmoove-Friedland has also?
No, that was different. In Friedland, we had the paper.
No, but he had before.
Yeah, but
As a conjecture first, and then proved using your methods. Sort of.
I think it was different formula. But
think it's the same.
they're all related. You know?
I think that,
Yeah.
I think it's.
I mean, once you have regularity, I mean, this is the natural
Yeah.
thing to do. So I would imagine this was done before. Yeah. Anyway, the point is then we can basically apply the same exact thing. We have some stochasticity properties, so we compute these marginals. They turn out to be some constant thing times 1, so we can just plug in 1. We get this. We have our polynomial for which capacity is easy to compute. We now have this thing, which turns out to be one of these non-degenerate real stability preservers. Okay, this is something like a polarized kth derivative, so we can apply the theorem to it, and we get some specific k value. And then we already saw that this counts k matching, so it has all the pieces we want, and you just put this together and you get everything you want. And I will say, I don't have really any time left, so I'm going to make one last comment about this. Okay, I'm going to put a bunch of stuff here. You can read this if you want while I'm telling this quick story. But maybe one of the more interesting things about this is this proof doesn't really require the correct intuitions. I gave you these intuitions about counting matchings, and when I originally wrote down that theorem that I showed you, I sort of emailed Gurvits because I thought he would be the one who'd be most interested in that result, and I said, what do you think this can be applied to? And he basically said, oh, I think you should be able to reprove Csikvári's bound. So I took his bound, I sort of turned it into some algebra, I then kind of just plugged it in, and it gave me exactly the right thing. And honestly, I had no intuitions about the matching. So you can either think of this as something cool in the fact that I didn't have the right intuitions, and yet I was able to prove this nice bound. That was kind of the tightest thing we had up until that point. Or you can think of this as sort of bad, that someone who didn't have the right intuitions was able to do something. I don't know. It depends on your philosophy, I guess.
No, it's good.
Well, yeah. Well,
you don't need gods. You don't need gods. You know.
Sure. Well, yeah.
Humans can do things. Because intuition comes from gods, you know.
So yeah. In any case, so it depends on your persuasion, I guess. But all to say, anyway, that's sort of how this came about, and that's kind of all I have. These are further open questions, but I don't really have time to talk about that. So.
Thank you very much. So, questions or other remarks?
Did you say anything about the proof? The proof is similar to...
So the proof, the proof is kind of right. I broke the proof of the way Gurvits did things down into this kind of induction. We don't need to use induction here because we just have a single operator, but that's also what made it more complicated, right? We needed some way that we didn't need to use this induction on the differential operator. So somehow, but we have all the pieces. We have the polynomial that represents the thing that represents our object and for which capacity is easy to compute. We have this differential operator. We know by the theorem exactly how it changes the capacity. And then after you apply it, you get some value that's exactly the thing you want it to count. And so that's that you get a bound by just putting the pieces together.
Have you ever seen any place where capacity has been used to prove upper bounds? And is it, a reason why it should not be possible?
I tried. And you can do something, but at the moment it's not the main tool. You can get capacity as a trivial upper bound. Capacity itself is upper bound, but you can play a little bit with that. No, it's probably requires more work.
There's also potentially something you can do where one of these inner product bounds. So you have some expression that's basically of this form. You have some P, Q is greater than or equal to some constant times capacity P times capacity Q. This is roughly speaking what this inner product bound looks like. And there's a way basically where you can set up these P and Q to sort of this inner product is some coefficient-wise product. And so the idea is maybe if all your coefficients are 1 and you do this, and you do some inner product, you're getting some sum of something. But then there's a way to, in the capacity, also to put the sum. So you get somehow a sum over here and a squared sum over here. And so then whenever you divide out by one of them, you get an upper bound. So there's some maybe way to do this. I've never seen a way to get something that's that
You won't
great
get-
out of this.
You won't get Bregmans that gets this way.
No, I wouldn't think so. So you can get some things, but it looks like they, at least in from what I've tried, it doesn't look like you can get something like that's better than what we know.
So you say that your constants are sharp,
Yes.
but wouldn't they prove Gurvits' conjecture on the convolution?
So they are sharp if you based on the individual degree of each variable, right? Which is something you might expect because in your characterization, right, you get a different one based on individual degrees. His conjecture is based on knowing just the total degree and not having to take into account individual degrees. That's the reason why you don't get it.
And what is the explicit formula for the constant?
For the constant?
Okay.
So if lambda is the vector of degrees of your variables, the constant is basically something along these lines. Where this is like, you get more variables here, so this is alpha in some of the variables, beta in the other ones, and then this is a constant that comes out of the inner product bound.
I can make a comment about this because I was thinking. So what is happening is roughly like this. That with these arguments, okay, you can get those things. They lead to results like Schreiber. Okay, but there is one weakness in Schreiber things which I kind of slightly overcame. That you don't get van der Waarden from Schreiber. Okay, my convolution of bound is a generalization of van der Waarden. And you would not prove it using Schreiber like thing, okay? So again, you need to combine those two things which worked miraculously for that result which I had this standard capacity. Okay? So again, this is things which would prove you like Schreiber things which won't give you van der Waarden without that extra improvement, okay? This is and I actually stated some kind of conjecture here, which explains it. But this is the essence of the problem.
So other questions or remarks? Okay, so
No, just one, just amazing work. So what I want to say, it's very beautiful. When I had this, when I proved that lower bound on the regular case, which was called like Friedland lower matching conjecture, okay. So I thought that there is, okay. I hope that there is a stable proof for that, okay, because my proof was not using stable original proof. And now there is this beautiful thing, and we should congratulate Jonathan.
That concludes today's discussion.